This is the Mohr's circle review from class on Tuesday, September 15th. And so we started by looking at this example from the text of Mohr's circle, where I have a normal stress of 80 units in the on the x face, a known normal stress of 0 on the y face, and then 50 shear stress, 50 units for tau xy. It is clockwise on the x face and counterclockwise on the y. And so we're translating this into Mohr's circle, and this is my stress element. So I come to Mohr's circle, and A, my point A here, is the condition of my x face. And so I'll see here that the text found, so 80, positive 80 units, and 50 clockwise. And so the text is putting clockwise shear stress on the positive y-axis and counterclockwise on the negative. So A is positive 80, positive 50, and B is 0, negative 50. And that's the starting point of Mohr's circle. 90 degrees rotation on my element translates to 180 degrees rotation on Mohr's circle. So it's twice the angle on the physical element. And so the point of Mohr's circle is to allow us to take a stress element and identify the principal planes of stress, which gives us our maximum and minimum normal stresses, as well as our maximum shear stress. And so once I've drawn A and B, my next step is to draw a line through A and B, and I can now find my center point. My center point is on the x-axis, or on the normal sigma axis, and is exactly equal to the average normal stress. So if I take the average of 80 and 0, my average is 40, and that is where my center of this circle is. And from there, I can solve my triangle that this side is an unknown radius. My y, my height, is 50, and my distance from the center of the circle to the horizontal position of point A is the normal stress at A minus the center. And so this is 40. So I have a 40, 50, and then this side turns out to be is the radius, and from this diagram looks like 64. So now I know my radius of the circle, and I can identify my maximum normal stress, sigma 1, my minimum normal stress, sigma 2, and my maximum shear stress. It's going to be equal and opposite at the top and bottom of the circle. And so we're going to pause here again, and this was the example we did in class, where a plane, a stress element is provided, and we want to find the principal normal and shear stresses using Mohr's circle. We want to label that circle and ultimately determine the angle from the x-axis to the principal normal stress. And I didn't highlight that, so I'll come back. This is the angle. I should say this is twice the angle that you need to rotate from the plane element, the plane given, to the principal plane. So sigma x is positive 20, sigma y is negative 10, and tau xy is 8 in the counterclockwise direction on the x face. So pause here and make some notes, and then we will do the example together. So this is my stress element. I have positive 20, negative 10. I have 8 counterclockwise, which means on this face it is 8 clockwise. And actually, so this is the one I did in my second class, but I think I had redone this with clockwise. You know what, I'll go through this one and then I'll show you the clockwise example. So I had put counterclockwise on my positive y, so this would be clockwise. And that means that point A here is 20, negative 8, and point B is negative 10, positive 8. And so A and B, I draw the line through A and B, and I find the center of my circle, which is the average of 20 and negative 10, or positive 5. I now know where the center is, so I know that the length of this side of the triangle, here we have a height of 8 and a base of 20 minus 5, or 15. Once I know 15 and 8, I can find my radius. And my maximum, or principal, stress here, sigma 1, is 5 plus the radius. Whereas the minimum principal stress, sigma 2, is 5 minus the radius. My angle to the principal stress, theta p, is represented here doubled on Mohr's circle, and the tangent of that would be 8 over 15. And so I can represent that here. And so I can find the angle to the principal stress plane. The last point I'll make here is that if I draw as the text does for clockwise positive and counterclockwise negative, I get the exact same circle, but A is positive and A is quadrant 1 and B is quadrant 3. Ultimately, my radius, my average, everything's exactly the same. The magnitude of my angle is exactly the same. I suppose I should mention as well that my maximum shear stress will always simply be equal to the radius of this circle, and the conditions of principal stress is that the shear stress goes to 0 there, and that therefore is the maximum and minimum normal stress that the element will experience.